Good morning, everyone. A little early for me, but that's okay. Oh, that's not too bad. 10:20, that's not bad. Everyone enjoy the party last night? I did. I found out I had queso on my little badge, so I wear it with honor now. So my name is Jimmy. You can find me on Twitter at @jbogard. All the slides and presentation materials, pretty much anything I do is on GitHub, so you can find that at github.com/jbogard. And I blog on jimmybogard.com. I used to blog on another site, Los Techies. You can still find a lot of my posts there. And there's some other junk about me. For my day job, I work at a consulting company out of Austin, Texas called Headspring. And I usually, for my daily work, I build systems for customers, build custom systems for customers. And a lot of what this talk is about is an experience with a customer I had in the last 6 months or so. So we had a customer, a manufacturing customer, which means, of course, they were an enterprise customer. And they wanted to move to microservices like you do, right? Like everyone is doing. If you're not doing microservices now, then you should just quit, right? That's what everyone's going to. So part of moving to microservices was they had a new partner they had acquired whose manufacturing model was completely different than what they were doing today. So they looked at their existing system and said, how can we incorporate this different kind of manufacturing into this existing system? Well, they couldn't. So they said, okay, we'll build a little system to the side that will integrate somewhat. We'll call it a microservice because why the hell not? It'll integrate with the existing system. Now, the DBAs heard about this and said, what are you doing? We can't put that other manufacturing system to the side. It has to go into this centralized database where everything is supposed to be. So long story short, they cut out the DBAs from the entire conversation and just said, right, we're going to build this on top of MongoDB. Because again, microservices, MongoDB, you have to do them together. They just go together. Well, as time progressed, they realized that they needed to get some of the more advanced features out of MongoDB. And then they went to the website to see, okay, looks like those aren't included out of the box in the free version. How much does the enterprise version cost? Well, it turns out the enterprise version of MongoDB is actually more expensive than the enterprise version of SQL Server. So they said, uh-oh, we've put ourselves into a bind here that we have this we needed these more advanced features and it's really expensive. What do we do? What they wind up doing is saving money by actually going to Azure Cosmos DB. So what is Azure Cosmos DB? Now, I'm trying to keep some of the marketing fluff out of here, but there are some specific things in Azure Cosmos DB that set it apart from other kinds of NoSQL databases. So Azure Cosmos DB is a globally distributed, that's important if you need that kind of scale, multi-model database service. So the idea is that I'm not just having some kind of document database I'm running locally and then I need to put it in the cloud. It's that I have some kind of system or application that needs to have global reach across the entire world. And so for this manufacturing company, they didn't need that because they had things like inventory and orders that were managed in a global ERP system, and they needed to be able to communicate with that. And so they had all of their different orders flowing through all their different manufacturing facilities worldwide. And so they needed this kind of global reach and global scale. Now, the second interesting part is the multi-model part. And this is the part that's kind of weird at first because I don't really think of a database as having different models and different querying capabilities. But the way that Azure Cosmos DB is engineered, it allows it to support different kinds of models and different kinds of data structures and different kind of querying APIs on top of it. So there are 5 ones they have today, and they say that there are more to come. Now, one thing I should caveat here is that you have to pick this up front. You can't mix models. You can't do something like a graph database and a document database together. When you're creating a new resource in Azure, you do have to pick this up front. So just pick the right one, I guess. Know what you're creating. I haven't seen this to be a problem in actual practice, but it is something to keep in mind. So the 5 models they do support, the first one's a kind of interesting one. It's SQL over JSON. So I have JSON structures actually stored in the database, but I can query it with a SQL syntax. So this could be good in those cases where you don't want to use a different kind of completely different API, and you have developers that are familiar with SQL, then they would be familiar with this kind of querying capabilities. And we'll see an example of this here in a second. The second one is documents. So this is kind of your traditional, jiggle. Oh, we're back. So this is your document database would be your just traditional like NoSQL database that you're kind of probably familiar with. With the document database though, one of the things they did was instead of inventing their own API and their own querying language for it, instead they said, okay, what's the most popular document database out there? Mongo. Okay, so what if we just implement the Mongo API and protocol on top of our own document database instead of inventing a completely new one? And so that's what they have here is the model is the document structure inside the database, and then the querying capabilities and the interaction capabilities are through a specific kind of API, in this case, MongoDB. So what that means is that I can actually use any kind of Mongo client to connect to Cosmos DB, and it just works. Most of the time. Almost all the time. There are some things that aren't supported for some of these APIs. It doesn't support every single possible operation, so that's something to look at. But what was really nice for our client is they were using MongoDB through their own hosted instance and said, we want to move to the cloud. And so they literally just changed some connection properties and the application just started working now with all their data in the cloud. Now this is not actually MongoDB hosted in the cloud. It is Azure Cosmos DB's special data structures and failover and replication structures behind the scenes. So they're not just hosting MongoDB for you. What they're doing is providing an API to connect to and query with in MongoDB. They also support columnar through the Cassandra API, tables, which was a little weird for me as well. So those of you that are using Azure Table Storage, which is anyone using that? I've met like one person that's ever touched Azure Table Storage. And so what that allows you to do is, instead of having your Azure Table Storage stored in Azure Table Storage, instead those tables can be stored inside of Azure Cosmos DB. And now inside of Azure Cosmos DB, you get the global scale that provides, which isn't provided inside of Azure Table Storage itself. And again, all you have to do is point your connection to Azure Cosmos DB instead of the other thing, and it'll just start working. And finally, it also supports graph models. So instead of just individual documents that are separate from each other, we introduced the concept of connections between individual nodes. And we can again query this using the most popular way of querying graph APIs, which is an interesting querying language called Gremlin. This is the one I had actually the most trouble with. We tried to move our own hosted graph that was inside a virtual machine inside Azure, which is like the most expensive, stupid thing to do, is to do VMs in Azure. We tried to move our Neo4j instance into this, but it turns out that we were using a lot of advanced querying capabilities that aren't yet supported. So that the Gremlin one, what you'll see is some of these querying APIs, they have a subset of the querying APIs that are actually exist out there. So you do have to carefully consider what kind of querying capabilities you need before just jumping straight and say, right, we're just absolutely going to do this. Now Cosmos DB actually started out as Azure Document DB. So Azure Document DB was this document database in the cloud. It was built on top of a lot of the pieces that Azure Cosmos DB had, and then as those extra pieces in Azure Cosmos DB, which wasn't released yet, became more feature-rich, then Azure Document DB just got folded into Cosmos DB as just one of the querying models available for you. Now, one of the big questions I get about Cosmos DB is, why should I use it? Should I just use it because I'm interested in doing some kind of NoSQL in the cloud? Well, maybe. But when it comes to the capabilities of Azure Cosmos DB, especially with its scale, it is priced accordingly. So you may start off using a simpler version or a more free version in some other hosting model, and then as you need some more scale, then you'll go to Azure Cosmos DB. Now, one of the most interesting things about it, of course, is its rich modeling capabilities. You don't have to just do document database. You don't have to just do one of these models. Instead, you can pick and choose what model is appropriate for you. Now again, this is scoped to the database, so you have to pick up front like which model makes sense for you. But again, in general, I don't really find people get confused about what kind of database they need. But it is nice that they have the major ones supported out there, whether it's key value, document database, columnar, or graph. And they're adding more. So the graph one, for example, was new in the last 6 months. All built on top of the internal structures of Azure Cosmos DB. The other major reason you want to use it is its global scale. So some of the announcements, even this week at Build, expanded its scale capabilities. So if you need applications that do truly need global scale, then you would start to look at some kind of NoSQL solution because those are the kinds of databases that can provide this sort of global reach. And so Azure Cosmos DB was built for those applications in mind. So when you go to the website and it says like, what are the kind of use cases, you'll see they'll talk about things like mobile applications, manufacturing systems where you have this kind of global reach. Anything that needs to reach on a global scale is something you should start looking at Azure Cosmos DB as a potential solution. Now there are a lot of existing solutions out there for these kinds of models. And so yes, you can use any of these existing solutions. What we ran into though is that when we picked one of these solutions out of the box, we were now wholly responsible for the server that's hosting this software. And a lot of this software is best run on Linux. And most of my customers have no idea how to manage Linux servers. Like they know how to use a MacBook, right, and run bash commands, but it's something completely different to run Linux servers at scale. So for them, they just didn't want to have to maintain their own servers and their own systems and have to learn how to manage these solutions. They just wanted to have the capabilities that these databases provided, but not have to carry all the burden of hosting these. So Cosmos DB provides this platform as a service offering that says, you can still have these kinds of databases, but now we will take care of all the hosting and management, and then you just get this nice, lovely API to talk to. Now, for those of you that already have existing systems and existing databases, it turns out you can already do some kinds of NoSQL in those databases. So you can do, and actually for the last 10 years, you can do kind of schemaless systems inside a SQL Server. So for example, you can have XML columns, right? That's a thing. You can put XML inside a SQL Server and query off of that. You can also output things as XML. So yeah, we've had NoSQL in SQL Server for a long time, right? You can just have it as XML. Well, I don't think I've never really met anyone that's actually done this, other than some people that decided to directly connect store procedures to SOAP web services, and they could just output the XML directly. But for most of my customers, they've never touched anything like this. Now, some new features inside a SQL Server, starting with 2014, I think, or probably 2012, are the ability to directly store JSON objects inside of the database. So for these, it has a kind of funny syntax. So you have this kind of weird looking JSON values and JSON or is JSON methods here. But I can use JSON queries to be able to look for individual values inside a single column that is storing a JSON blob. So instead of what I used to do would be to serialize JSON and store it in like a byte array or something like that inside a SQL Server, but you can't query that. And so now SQL Server exposes directly the ability to store JSON as values inside the database and has first-class querying and selection capabilities out of there. So if you have an existing system and you need some things that are schemaless, I would look at these kind of things first, because it's much easier just to use whatever you have already than to introduce something that now is going to have to involve procurement, because we have to ask procurement for the money to be able to purchase and deploy Azure Cosmos DB. So that's something I would look at first is, can we just get away with storing things inside of our own database before we start looking outside and going to something more complicated? Now, for scale, SQL Server does support the idea of failover clusters. So if the master or the primary goes down, then it could fail over to a secondary. And the more expensive versions of SQL Server support the idea of a cluster of failover machines, so that if a primary goes down and then another machine goes down, there are multiple ones that it could fail over to. This is like super expensive though. That's like the most expensive checkbox in the installer known to man. Like you check the box for the SQL Server always on, it's like you better have your wallet open, because the Microsoft licensing people will be right at your door ready to charge you for this sort of stuff. So you do get this failover capabilities, but the other thing we run into is that these replicas have to be very close to that original instance, which somewhat defeats the purpose of having global scale if all of the machines have to be very close to each other. What I want is to not have to worry about a single server going down or a rack going down or potentially a whole server farm going down or entire location going down. I can still have my application up and running, especially for mission critical applications or ones that do have to reach that global scale. Now they have relaxed the licensing somewhat on this, so if you do need this always-on capability, it now is supported in the standard version, so it's still expensive, but not so expensive. But if we want something that can fail over to multiple machines, that's again only the enterprise version, which again, you have to have your wallet out to be able to pay for that kind of thing. So with our group, when we moved from going from SQL to MongoDB and eventually to Azure Cosmos DB, we had a lot of bumps in the road to be able to make that transition. Now, in transitioning from SQL, we were able to effectively cut out the DBAs from the conversation. That did come to bite us later on when we needed to actually report out of the system and found out that MongoDB charges for reporting. Oops, probably should have looked at it early on. But SQL is modeled very differently from any kind of NoSQL offerings. So in a typical modeling session we start to look at the major nouns in the system to say these are going to be the tables. So in this case, I have like a product table, and then I look to see what that thing is related to. So it's going to be related to, in this case, I have categories, so it's going to be related to categories, some model information, descriptions for translations, health, cultures, things like that. And one of the nice things about this model is that it's a very flexible querying model. I can start at the product level, I can go out to one direction, I can start from a category level and start to pull in other products. So it provides a very flexible way of querying over my data. That's both a good thing and a bad thing, especially those of you that have used ORMs, and then also have used ORMs in the presence of a database administrator, and then they see the SQL that's being generated, and they come and yell angry things, take away your ORM, and then only give you store procedures from there on out. So while this provides a lot of flexibility, it also comes with a lot of responsibility to really understand what you're doing behind the scenes. The other thing that we found with this sort of model is it doesn't really enforce a lot of constraints that we were wanting to. So we wanted to make sure, for example, that when you add an order and a line item, that the line item's total always bubbles up to the order. So you can do that pretty easily in code, but it's difficult to model that kind of relationship inside of a database. You do things like triggers and stuff like that. When I'm just looking at it, there's nothing telling me that those kind of constraints are in place. It's just kind of a big mess of tables, and then you have to figure out like what is the right direction for me to start traveling in these different relationships here. So in a NoSQL scenario, we model things now much differently. Instead of having things that we can join to, we have to make sure that all the information that we're interested in has to be stored inside of that one document. But inside that document, we have now a much richer data structure that we can work with. So in this case, I've got an example of an order stored as a JSON document inside a SQL Server or inside of Cosmos DB. Now, if I was modeling an order, typically, I would have an order table, and then I'd probably have a customer table to link to say this customer purchased this order. So that way, if the customer has multiple orders, I only have one customer in the database instead of that duplicated through all my orders. And if I have line items in my order, of course, I'll have another line items table. So I will have the line item plus the product ID of the product they're purchasing. And so in order to get the full view of a single order, I'd have to query, like in this case, let's see, the order table, the customer table, the line items table, the product table, at least 4 tables I'd have to join together to be able to get this view. Now most systems that I work with, that's on the way low end of joins that I have to do to be able to show some information on the screen. Typically, I see queries with like 8, 9, 10 joins to be able to get the information and be able to view it on the screen. Now, for a lot of SQL Server instances, that's not that terrible. You can always just throw more money at the server to make it beefier and beefier. But for this one, when everything is on that single record, I only have to make one connection, make one query, and it returns that one single result, and I don't have to connect to anything else inside the database. So that entire model is stored in one single record inside the database. I don't have to go out and pull in a lot of other pieces of information. Everything's stored inside of it. Now, because it's JSON, JSON supports complex structures, like having a customer object with child properties. So I can go order.customer.firstname, order.customer.lastname. I don't have to first denormalize that to store it into a flat table. So if I tried to store this in one record in SQL Server, I would have like a customer first name and a customer last name if I wanted that to be on one single row. I can also have arrays inside of my object as well for these one-to-many scenarios. And again, I don't have to do a join to be able to get this information. Everything is pulled back when I pull back this one record. I don't have to go out and pull out other records from other places. If I need to connect to other places for some other reason, I can still store the keys as just individual data values inside of my document. So in this case, I'm storing the product ID for the products for those individual line items just directly inside of my record here. And then if I want to go pull out that product ID or pull out the product related to this, I can't do that inside of this database. I'd have to make additional calls to be able to get those individual records. So that's something to keep in mind, is that when I'm designing these kinds of data structures, I'm designing them so that I only need to make that one call to get all of the information I need. And if I do need to make other calls, then I understand that there's a penalty for that. I have to make additional calls to get those additional pieces of information. So no joins inside of here whatsoever. There are projection capabilities, but you can't join two documents together. That's just not how it's designed. So you have to build everything inside of this one record. So you have to really understand what you're designing and what you're building to make sure that this document is designed correctly. This is one of the big things that we ran into in our first foray into document databases. We designed a lot of them incorrectly at first, and it was difficult for us to migrate those data structures to new data structures over time. Because it's schemaless, it can be difficult to say, well, what are all the bad records in my system that have the incorrect kind of data structures, and what are all the good ones? Well, it's not that easy to do. You have to literally query over all the items in the system. So something to keep in mind, schemaless doesn't mean there's no schema in your system. The schema exists, it's in your application, not in the database. So something we found out the hard way. Now, there are cases that we do want to duplicate some of that data. So in this case, I don't want to have to go back to the product database to be able to get this information, just to show the order on the screen. So there were cases where we looked at immutable data, that is like data that doesn't change over time. Instead of us needing to go back to the original systems, if that data is only written once, then we found it was okay for us to go ahead and include that information in our document. I'd be super careful about this because you really have to understand if that other information changes. Do I need to have it updated here? And if it does need to be updated here, then that's when you would never want to do this. If you have to have the data updated in both places, then just don't do this kind of thing. But for something like product information, where we saw that that data is really just written once and never changed again, then it was okay for us to cache it locally inside of our document here. And that way we don't have to go back to the product catalog system, which was still a SQL Server database. So the other thing we've noticed is that just because I'm copying the data does not mean it's actually duplicating the data over time. We'll have an example of this. So I worked at an e-commerce system for a while, and the overall e-commerce value stream, if you will, was you go online, you shop for some items, and we call this the catalog. When you want to purchase an item, you put the item into your cart. So you say add to cart. So something like a product price, we'd start out with, okay, I see the product price as $24.99, and they add the item to my cart, and now it shows up in my cart as $24.99. When I hit checkout, I now go to an order screen, and I see again that price there, $24.99, in my order price. And then finally, when it gets down to fulfillment and billing, they'll see that same price again to know how much to charge me eventually. Now what happens in this scenario when the product price changes all the way up in the catalog side? Does that mean we need to change the prices for every single system that had that product price as part of it? Did these other systems actually have to go back to the catalog to get product pricing for every step along the way? Well, no, they don't do that. In fact, you probably think it'd be really weird or honestly infuriating if I'm sitting in my cart and the product price changes and the price changes in my cart. That's probably something you don't want to have happen to your customers. So in this case, even though the data was copied from location to location, that didn't mean that it meant the same thing over time. So when data moves between service boundaries, and when it crosses that service boundary, sometimes its meaning can change. And so in this case, the price we had along every step of the way was not product price anymore. We had a catalog price, we had a cart price, we had an order price, and then finally we had the billing price or the fulfillment price. So this was the amount we actually charged the customer. Because in any step along the way, if I want to reason about the price at that point in time, I don't care about what the catalog says today. I care about what the price was, or is in this step of the process. So in this case, even though we were copying the data, it didn't mean the same thing anymore. It didn't mean the product price anymore. It was the cart price, the order price, or the fulfillment price. Didn't mean the same thing. Now, I did have a customer that didn't like this. They saw this as duplicate data, and they said we can't have any duplicate data to the system. That's the bane of our existence, is duplicate data. So what we'll do is normalize everything to some other nth normal form, because there are normal forms past third normal form, by the way, if you haven't had the privilege of seeing those kind of databases. So how do I get the price then in my order if the product price can change? And the way they tried to solve that was to put active dates on all of these fields to say price as of this specific date. So when I joined from my order back to the catalog to get the product price, because we can't duplicate it, I had to pass in the order date to know what the price should be as of that point in time 2 months ago. Or I could just copy the price from location to location, realize that it's actually changing its meaning. It's no longer the product price, it's something else. And then everyone is happy. Well, except for that one DBA, but he learned to live with it. One other thing we found with SQL databases is they do support this concept of relationships. So in this case, I've got relationships between product and product photo and product model and product subcategory and unit measure. But if I want to get information about those relationships, that's really difficult to do. So in this case, I have links between these things, but I don't have any information about those links. So in more complex scenarios where I want to include information about the relationships, that's when SQL starts to break down. And I especially see this when I have a graph of things and I want to relate them to each other. You can do those in SQL Server. The things like common table expressions. Can anyone do that out the top of their head? Liars. We'll have a quiz after class. We'll see if that's actually true. So you can do kind of recursive joins and funny joins to build graphs of things, but it doesn't come back as a graph. And if you want to query those relationships, it's pretty difficult inside a SQL Server. So you wind up creating tables to represent those relationships, and now your joins become really weird and ugly, and you start to have lots of weird cardinality and lots more rows that are returned because it can't really represent the different nodes versus different edges very well inside this one single kind of structure. So you see these kinds of relationships a lot in things like social media apps, right? You have Facebook or LinkedIn that says who you're connected to or who you're friends with, and then you have information that could be then stored along with that relationship as well. So if I want to query those relationships, like if you go to LinkedIn and you search somebody and it says like you're 3 steps away from that person, that's best answered with a graph database as opposed to a SQL database. Yeah, there we are. So I don't build a lot of social media apps, personally. I try not to use them except for things like beer check-in apps, things like that. But what I do a lot is track history of things. And probably the best example I have to be able to track history and make these connections is Amazon.com. And if you go to the Amazon.com website, just look at any kind of product page and start to scroll down, you can start to see the other kinds of information that can be pulled out by having connections between different things. For example, things like frequently bought together. So I'm looking at this one. This is the Amplify, which I highly recommend. It's a really awesome home networking device. And it told me that when someone buys this thing, people frequently buy this other thing. Now, try to imagine how you would answer that question inside a SQL Server. That is, you have orders and line items, and you have to go traverse like go find all the line items, and then go find all related items, but then do a weightings that says, make sure I count how many times these different items are purchased together, and roll those up and find me the top one that is going to be shown here. Like, you can probably write that query, but it's not going to return very quickly. So a graph database who is connecting orders and line items and saying when someone buys this product, they also buy this other product, and then start to include like how many times people bought these products together, then it's a very easy query to return back from a graph database. I can even track behaviors for customers who are just going through the website. So instead of orders in the system, things like if I'm looking at this item, who else looked at it? Like what other stuff are people looking at? So as you look at things inside of Amazon, I don't think it's tracking in the browser. because that's wrong, right? Tracks you on the server, and on the server, it's keeping track of what your overall history is and says, okay, you looked at this item, you looked at this item, you looked at this item, and then it aggregates for one item, what are all the other stuff that people have looked at and said, here are the top things that people have looked at who also looked at whatever you're looking at right now. So I use this quite frequently to say, okay, I'm looking for this product, but there's a lot of competing products. I don't really know which one's the right one, but this will tell me what are some other related products, and also can tell me the price and reviews, so I can see that, hey, oh, this other one is actually reviewed much better by a lot more people, so maybe I should go look at that one instead. Again, you can do this kind of query in SQL Server, but it is very, very difficult and expensive. And then finally, you have something like customers who bought this item also bought. So the first one was frequently bought together. So that is, in a single purchase, what do people typically buy that together? This one is looking at order history that says, when people buy this item, what other orders do those customers have? And what commonality do those different orders from those different customers have? So in this case, we have customers who bought this thing, also would go on to buy this old switch, I guess. I find that highly dubious. Maybe they started with a switch, and like, ooh, that's, I don't want one of those things. I want just Wi-Fi, so let me do that. But again, trying to do this inside of a relational database is just a very difficult thing to do. So as you get these like really weird marketing questions about, hey, can we run a query to do this? You're like, okay, we can do it once, but that's it. If we want to do this every time someone looks at something on a screen, then we have to build something special to be able to take care of this. So these kind of queries just absolutely blow up the overall SQL model, and you wind up having to go to other more rich models with the graph database. Now, this is when my customer realized that SQL wasn't going to work for them and started to move toward graph databases. This is probably the biggest transition that they had, because the querying capabilities inside of graph databases are way, way different than anything else I've ever used. It uses a special language called Gremlin to be able to execute graph queries. And Gremlin is a language written in Groovy, which is an actual programming language, not a, never mind. And so in this kind of graph database, I don't just have individual records by themselves. I don't have just the individual record that has all the data. I don't have to have just that. Instead, I start to connect those different nodes together. So in this case, I've got different people with different connections. And those connections can also have names. So instead of just saying, like, this is related to that, well, how is it related? What is that relationship there? So in this case, I got things like Marco knows Josh, or Josh created IOP, Java, something. And Peter also created that as well. So I can have different nodes with different kinds of relationships, and then also have values and attributes on those relationships as well. So as I traverse the graph, I don't have to just follow connections. I can also look for connections with certain values, and certain distinctions, and certain types to be able to figure out how these things are related to each other. And the final thing that we ran into was another somewhat difficult transition, was transitioning from transactions in SQL to transactions in NoSQL. Transactions in NoSQL, for a lot of NoSQL databases, it's more kind of a like optional sort of thing that people do. Like, oh yeah, we kind of do transactions somewhat, but they really don't do that many transactions. But transactions in SQL start with this, right? ACID, which is atomic, consistent, interesting, and durable. Something I forget. And it all comes back from a series of papers written like 35 years ago or so. So in an ACID database, and one that supports these kind of transactions, you can do things like this. You can begin a transaction, you can do multiple sets of operations, and then you can either commit or roll back that operation. When you commit that operation, either all of the changes go or none of the changes go. And the idea behind the D part in ACID says that if partial changes happen, it'll roll back the other changes as well. So if something happens like in between here, it'll roll back those intermediate changes. And finally, you can actually roll back the entire transaction as well to say, undo all of these changes. So what do you typically do when you start to look at, okay, this NoSQL database, I want to use it. Does this thing support transactions? That actually comes up on the FAQ for Azure Cosmos DB. It says, does it support transactions? Yes, it does. With JavaScript store procedures and triggers. combining my three favorite things: JavaScript and store procedures and JavaScript triggers. That's one of those like, did you just tell me to go F myself? Now, the reason why they do this, of course, is that the data structures inside of Cosmos DB are JSON documents. So that's JavaScript. So why not use the language of the data structures as the language to do these procedures? And then finally, why do store procedures for actual transactions? That if I want to modify multiple records at the same time, well, I need to have that code executed as close to the data as possible. And the only way I can do that is to put that code in the database via a store procedure. Now, I won't show you one of these things because I can't fit them on the screen. They're so big about how to do these kind of store procedures, but they do exist. We looked at them and saw how difficult they were going to be to use. And then we also knew that if we had anything called a store procedure, someone in the DBA land would be listening on our emails, put their head up and say, ooh, now I can help to write store procedures for every single point of data access. So we didn't want to do that. We said, okay, yes, this is possible for us, but we want to treat this as a last resort. So what can we do otherwise? So one of the problems of doing a transaction between two different records is I don't know if those two different records are necessarily on the same machine anymore. In something like Cosmos DB, I don't care where that individual document is stored. If document A is on this machine and document B is on that machine, I don't care at all because I'm only querying one document at a time. But now if I want to do a transaction between those two different documents, now I need to coordinate those two activities. And I could do that via a store procedure that's executed like a highly coordinated activity, or I could start to look at what does it mean to not do these kinds of transactions. And this kind of transaction where I'm having to deal with two different operations are also known as distributed transactions because I'm transacting between two different records on two different machines. So there's this great paper by a fellow, Pat Helland, who basically, he was on the SQL Server team. He actually built the distributed transaction stuff inside of SQL Server. And then he had this epiphany when he moved to either Amazon or was it Salesforce, where he's like, oh, you can't do this at these cloud scale operations because I can't put the entire world in transaction. So what would it mean to move away from these sort of things when I only have these individual records I can deal with? How do I coordinate activities between these two different records? Well, his brilliant idea was to use some kind of messaging to transact between these two pieces. So the idea is that when I have a transaction between these two entities, instead of me trying to mutate both at once, I mutate the primary one and store inside of it a message that says, I also want to mutate this other one over there. So that way the write only happens with that sending entity at one point in time, and then later on, when my message finally gets delivered to the receiving entity, then finally I can go ahead and perform the operation in that second one. Now, there are some problems here. My transaction can only be around one single document at a time or one single entity. So how do I deal with like taking a message from one entity and giving it to the other? Well, I have to now keep track of these conversations between entities. So as operations build up over time, I keep track of the things I've done with other people. So I'm receiving messages, storing them, and keeping track of them so that when if I happen to receive the same message again, then I can say, oh, I've already done that, nothing to do. So each of these entities uses messaging, but a special kind of messaging in which the messages are stored actually inside the document itself, and it uses those internal document messages to communicate to other things. Now, when we looked at this, we said, that sounds awfully familiar. This idea that I have documents or aggregates needing to communicate to other documents or aggregates. And if you've been around domain-driven design much, this actually is a first-level concept inside that world, and it's known as domain events. Domain events, and what I can do here is I have a single document. In this case, I have some order here, and that order has all the attributes of the order. So it's got the first name, the customer information, the line items, the price, the total, all that sort of stuff is inside of there. But if I need to communicate to any other entities, instead of me doing that directly, I'll keep track of that communication with an inbox and an outbox. An outbox is messages I want to give to other entities, so I need to do something to that thing over there, so I have a message in my outbox over there. And the inbox are messages that I've received and processed. So when I get a message that says, I need to do this thing, then I look in my inbox and say, have I already done that thing? If I've already done that thing, then I say, nothing to do, nothing to do. If I haven't done that thing yet, then I'll go ahead and perform whatever operation I need to do. I will add that message to my inbox and perform one save operation that writes my entire document, and I'm done. Now, as I communicate to these external records, then I'll just delete my records out of my outbox. And we found this worked really well for the document database. So the messages themselves could just be other JSON objects. And as long as I kept track of what the communication I had, then it was really pretty straightforward for me to interact with other aggregates without having to do something like a store procedure inside of the database. Now, I haven't found any kind of tools or frameworks that do this kind of thing out of the box, so to speak. So we did have to write a lot of infrastructure code to be able to support this kind of model. But in the end, we found it was worth it because I no longer had to care about, oops, some developer accidentally tried to write to 2 documents at once. What happens to the second document? It just goes away. Oops. So with this model, we were able to pretty easily interact with multiple documents at once and not have to worry about the transaction side effects. Speaking of transactions, even the consistency models inside of Cosmos DB are much different than SQL Server. So SQL Server has these consistency models that basically protect your information. And most people don't actually use the highest level of transactions, the serializable. Most people use things like repeatable read or read committed. Snapshot is somewhat expensive, so that's optimistic concurrency supported inside of SQL Server, but it does have an expense associated with that in terms of resources. So these people can get away with repeatable reads so that I can read my own writes, but I won't see necessarily other people's writes yet until their transactions are done. One of the other things we found is that most of the time, our transactions aren't actually ACID. That is, to the letter of what ACID is. So this was a report from Peter Bayless, who looked to see what are all the actual consistency models supported by the major relational databases out there, and what do they default as. And what we see is that actually most databases don't even support ACID transactions, that is serializable transactions. Most have some lower version of it. And then most as well don't even have serializable as the default option, because serializable is actually really expensive to do. It can block reads from that row, so you want to be very, very careful in doing these kind of operations. So Cosmos DB has a similar kind of concept, but it's something that's more tuned for cloud scale operations. So they have a tunable consistency model that basically goes from strong consistency to not weak consistency, but they call it eventual consistency. And a strong consistency, that means that I'm guaranteed to have the most recent version of an item. I never read any stale items ever. Now for systems that I'm always updating, maybe that's something that I really want to have. Like if there's some precious resource that everyone has to have the most updated version, then I can do that one. Typically people do something like a session-based consistency level, which means I can read my own writes. Writes will follow a previous read. And then it's just like most normal operations, that's pretty staying default. And so I think like 80% of people use just session level consistency that just says, for the context of this connection, I expect inside that connection that everything should be consistent for those communications. Now, if there are other connections and other sessions other people are doing, they won't necessarily see what I'm doing, but at least I can see what I'm doing. And that's what most people really want, is to be able to see the work that they're doing and not really care about what other work other people are doing. So I want to switch over to a demo to show you some of the capabilities of Azure Cosmos DB. So I'm going to first just go through just a little example of what it's like to actually create one of these resources inside of Azure Cosmos DB. And switch to duplicate. OK. So I will go ahead and create a new resource. And this will be a Cosmos DB, one right there. And let's call it something good. And this one I'll use the document DB API. So let's call it NDC Minnesota 2018 Mongo. And the API I'm going to choose, again, I have to pick something here. So I'm going to pick the MongoDB API. I will use an existing resource group. That way it's super easy to delete all these expensive things when I'm done. And then here's some other interesting checkboxes you can do. You can enable geo-redundancy, which means that my data will be stored on multiple different regions across the globe. And then finally down here, this is the thing that was announced just recently at Build, like Monday or Tuesday, is multi-master. That is, if the master node goes down, the client doesn't know about it and will automatically fail over to another node. And I can start writing to that other node. With the other one, I can read from multiple nodes, but I won't necessarily be able to write to multiple ones. In this one, I can actually write to multiple nodes. So when that one node goes down, it will automatically fail over to another one. There are a lot of academic papers behind the work behind how that happens behind the scenes. So I'd encourage you to go to Microsoft's documentation on this because it's really well done and really well written on how this actually happens. But I'm going to turn that off because I'm not going to turn that on because this is another expensive checkbox that I don't want to check right now. And this one is a preview feature, so you actually have to say, I would like this. They don't have to turn it on by default. Okay. All right. So while this is going, some of the other things that we found working with Cosmos DB, going from Mongo and then going to Cosmos DB, is a lot of the client APIs work just fine. So for MongoDB, for example, there are already existing .NET client APIs to be able to work with it. And literally the only difference for us was a connection string to be able to say point from this to that other thing, and we were good to go. The problems we did run into, and we did run into a few problems, is that MongoDB's API does support the concept of updates inside of a query. So I can say, do like a for each on these things and do this little update for each of those. So it has this atomic operation inside of the database. So there's more advanced features of these APIs that are atomic write operations inside of the database. I found that none of the APIs really support that. They want you to use the client API to do that, not a query API inside of the database. It's just too complicated. So we did have to fix those to do that kind of work in code, as opposed to submitting a query inside of the server itself. Should have known in Azure talk, nothing was going to happen. Oh, whoa, it worked. Okay, it says, congratulations, you did the thing. So some of the interesting things we can do as part of this is we can actually download, some of these can actually let you download existing sample applications to be able to connect to it. But it'll give us a connection string, so I would literally just copy this and put it into my Mongo client connection string, and I'm good to go. Some of the other ones I found actually give you nice quick starts. So in this one, for example, let me go to the Data Explorer. They give you an ability to actually query things directly inside of the Azure console here. So in this case, I'm executing, and this is, yes. I'm just returning back all the items inside of my database here. And so I've got an array of items that says, here's this product, here's this other product, and here's then a link between those two products. Here's another existing one I had going on. And this one executes as a Gremlin query, that really funny thing to be able to connect things together. And so as I look at the different nodes and values inside of here, I can see that over on the right has here all the edges associated with it. So I'm looking at Ben, and then it's connected to Robin via this nose target. So looks like Ben knows Robin. Okay. If I go to Robin, then I should see the other direction. That I am the source of it, that Ben knows me. It's really small, so I can zoom in. Nope, that didn't do the desired thing. So it gives you a way to be able to play around with queries directly inside of the browser if you're going to load up some other kind of querying tool capability. Now, all of these different kinds of databases do have kind of standard querying tools available for you. So you can just, like this one, for example, there's a Gremlin console. You can go to connect to this and execute Gremlin queries. Same with Mongo. You can go to the Mongo console. For Cassandra, there's their own console as well. All right, so I wanted to show an actual example of me trying to build an application as well. So in this case, what I've done is I built a e-commerce application to show the capabilities of the document database. Now, this e-commerce application has two parts. One is the catalog to be able to browse the different items in the store. So let me go ahead and run this. Now, the catalog side, I actually just pulled from AdventureWorks. You know, that old demo database that Microsoft put out that showed you how to build relational databases. I didn't feel like inventing my own with a bunch of dummy data, so I just pulled theirs. And this is what they have here. So up at the top, I've got the list of product categories. I can go click one, and it shows me the list of subcategories. And then finally, I can view the list of items. I can add these individual items to the cart. So you can see over on the right, it's filling up my cart. I can also view one of these individual items and also add that item to my cart as well. So looking at how those different pieces are put together, I can go to my different products pages. The list of products is not that interesting, but one thing you will notice here is that I have to actually do this include because I'm going from product category to product subcategory. Because I'm showing these two items, I have to do an include that will perform that join for me. So that's not too bad. What about listing products? Well, in this one, I'm starting from a subcategory and then showing product details to be able to add the product, show the product information. So in this case, I'm going product subcategory and then joining in the product information, finding the one that's just that one single product subcategory. Again, that's not too bad, right? Like just a one-to-many there, not too bad. It's the show where things start to get kind of interesting. I had to join multiple tables down. So in this case, in order for me to show the description on the screen, I have to get the product information, then I have to join to the product model, and then to the product model, product description culture, and then finally to the product description table to actually pull out the product description for the culture that I'm looking at on the screen. So 1, 2, 3, 4 joins to be able to show this on the screen right there. Which again is like, it's not too bad, but I'm just showing this one piece of information. As this screen gets more complicated, that's when I start to see the joins explode in my system. And again, I can keep throwing the money at that SQL Server to make it get faster and faster, but it does reach an upper limit where this kind of approach doesn't work anymore. So let's see how I did the actual ordering part. So let me go back to my cart. I'm going to hit, my cart went away. I picked the in-memory session, and I think it just goes away after a time. Okay, so I hit checkout, and now I'm looking at some order details. So let's look to see what the checkout actually did. So in my cart controller, when I actually perform the checkout, that's what we have right here. So first, what I'll do is get the cart information. For me, I could have stored this in something else, Azure specific, but I was lazy, so I just stored it inside of session state. So it's just getting the cart out of session. And then from there, I'm going to store that order inside of Azure Cosmos DB. But instead of me storing an order with order line items and a separate customer as all different things, instead I'm storing it as one single item, one single document, one single record. And so that right here is this order request. The order request includes, in this case, this is just dummy customer information, whatever. And then also includes the line items. Now the line items will copy over some of the information. Again, the information it copies over is the information that either doesn't change over time, so it's immutable, or it's data that actually changes meaning as I go from one overall step to the next. So in this case, I'm copying over the product ID, so if I ever want to get that original product information, that's good. Then I have the quantity from the cart, of course I need that. I'm pulling over the list price, because then I don't want changes in the price affecting my order whatsoever. And I'm also pulling over the product name just because that's something that doesn't change, so it's an easy thing to do. Then I will call into Azure Cosmos DB, and I just have a kind of a simple wrapper on top of this. This is using a repository pattern. And that implementation, it's a pretty straightforward call. I use this create document async, and then builds up some information about exactly which database and collection to put this thing into. And then finally, the item itself is just a .NET object. So that .NET object will be serialized into JSON when it goes into the database. So pretty much, in terms of what data structures it supports, just all the normal things that Newtonsoft JSON supports, just don't get cute or clever. Just keep things simple, and then everything will work out okay. Okay, so at this point, my order is inside of Cosmos DB. But notice there was no like begin transaction, begin session, commit transaction. Once I make that call right there, my order is inside Cosmos DB. So from that point, I need to go ahead and clear the items in my cart, put that empty cart back into session, and then finally I'll go ahead and redirect to the show order page for that order that just came back. This document came back with that ID, so I can say redirect to that order with that specific ID. Now when I go look at my order inside of Cosmos DB, you can see what it created. That wasn't the right place. Where is my, there's Data Explorer. Okay, so here's my collection of, or the database of order requests. And then from there, I have the collection of items. So a database can have multiple collections. You can kind of think of them as tables. I don't want to store just everything inside of one collection because I can't reason about it. So in this case, I just had order requests as a top-level database and the order request items as just that one collection I have as part of that. Then, if I want to see all the orders that exist, right here it's turning back 4 results. So I have 4 existing orders. And this one that I just did was a total of 3399.99. So, oh, that's this one right here. And it said I purchased 1 single mountain bike with this product ID with the quantity of 1. And of course, everything's stored as that single array of items. And my customer information, again, is a more complex structure. So I can have customer.firstname, customer.lastname. And then finally, there's some other junk that's internal database stuff that I don't really need to worry about. So you can't name things those. So if you really wanted to name property _self, you can't. I don't know if you would want to do that, but there are some reserved properties that we have there. So one thing I should note here is that I actually picked the SQL version of the API. So up here is a SQL query. So I can do something like select star from C, where C dot, let's see, status equals 0. 0. This told me it returns 3 different orders. I can look for the status of 2, which means it's been approved, and I only see 1 order being returned. So back in my application, I can actually approve the order. So let me go ahead and click approve. And now you can see, yep, the status went from new to approved. And if I rerun my query, I'll see that. Yeah, now I have 2 orders approved. And down here is my second approved order right there. Now we're turning this item back in the screen for showing the actual order. I have over in the order, show order page here. I'm using that same document database, document DB repository. And then when it returns the item, it just does get item and deserializes that item from JSON into this strongly typed order request object. And now I have this much richer order request object to deal with. So I've got all the line items, the status, the total, the customer information. I can now show that on the screen. So if I want to include that information, I can do order.customer.firstname. So it's still strongly typed. But schemaless. So I have some object that does represent what is going to be put into the database. But if I want to change that object over time, I don't have to do schema updates to do so. I can just add new properties, get it serialized, and I'm good to go. Now, I will say that one of the things we did run into is we actually did at one point in time need migrations for our database because we needed to change the structure of what was in there. And there's really nothing out there that is for migrations of document databases. There's nothing that helps you with this specific, with this problem here of what happens when I do something like add customer middle name. What about all the existing records with customer middle name? Well, do I just ignore it if it doesn't exist? I need to make sure the deserialization doesn't lose that information. If it's required information, what do I do with all the existing stuff? So all that kind of stuff we had before. Those kind of problems still exist for us. We just have to do them now in code to be able to fix those scenarios. So that was our last lesson we learned was even though there was no schema, the schema still existed. It just moved to code as opposed to being inside the database itself. So we still have all the problems with schema changes over time, but we had to write some of our own tooling to be able to support that. So if you have more questions, Microsoft's website is fantastic for this. So I'd say start there first because they have a lot of great tutorials to be able to just download samples and get going from there. In terms of pricing, that is another thing that I didn't even try to go through, but read carefully how the pricing works because it is very different from other kind of offerings inside of Azure. And so that is usually the limiting factor of why people don't use Cosmos DB is because they're just running MongoDB locally, and now they want to go to the cloud, and they're like, oh, wait, this is for like globally distributed applications, and it's priced accordingly. So something else to keep in mind. Otherwise, if you have any questions, I'll be around afterwards. Otherwise, thank you very much, and have a great rest of the conference. And of course, don't forget to rate the session out there. The red and yellow ones are broken. They're not working right now, so just the greens, please.